Hello everyone, my name is Naveen Dar. I'm a high schooler from San Diego, California, and I'm very excited to present to you all this project towards real-time rainforest gunshot detection. So wildlife poaching is still a severe issue with many cascading consequences. It can lead to species decline and extinction, causing ecosystem-wide destabilization, leading to a loss of ecotourism revenue and a cultural heritage loss that cannot be assigned a fiscal value, making it one of the leading contributors to global biodiversity loss. However, even as poaching continues, potential for acoustic monitoring is rising in helping us understand where and when poachers hunt. But still, it's only a game of cat and mouse between the rangers and the poachers. What if there was a way to detect poachers autonomously in real time for a low cost, allowing immediate intervention? Passive acoustic monitoring may hold the answer, but we'll have to make some modifications first, because existing systems usually use large neural networks that cannot be deployed for edge deployment, and literature indicates high false positive rates in these rainforest environments, making these systems retrospective. So my research addressed these two bottlenecks by creating a lightweight model from the ground up and investigating sensor confidence integration as a way to reduce false positives. The datasets I used were a training and validation dataset from Belize, a test dataset from Vietnam, and a dataset from Africa collected by the Elephant Listening Project. Investigation into these datasets revealed large variance across gunshots in signal-to-noise ratio, shape, and frequency ranges, but some features remained constant, and I used these features, the spatial, onset, and temporal features, to infer what neural network layers I should use. Additionally, the input can make a big difference, so I settled on classic log-meld spectrograms as they also highlighted gunshot features while reducing input size. To help the model generalize, I employed extensive waveform-based augmentations and root mean square waveform normalization to help the model be invariant to different gain settings, mics, environments, etc. The final architecture consisted of 2D depthwise separable convolutions, 1D convolutions, and a gated recurrent unit for temporal feature extraction. Sensor integration. What's the motivation? It stems from the fact that most false positives are lower energy acoustic events, like branches snapping or rain hitting the microphone. And so I hypothesized that a sensor analysis and integration layer, or SAIL, can help to reduce them. Illustrated by these two examples. On the left, you can see that a nearby false positive fooled one sensor, but because its signal doesn't have enough energy to propagate through kilometers of rainforest, the entire array confirms no gunshot presence. Whereas in the case of a gunshot, because it's a higher energy signal, it propagates further and is picked up by the majority of sensors, confirming gunshot presence. The function I ended up on boosts agreement across sensors, penalizes confident isolated predictions, and is scalable to any amount of inputs. To evaluate SAIL, I used random gain, Gaussian noise, and time shift transforms to emulate a wide variety of 3 sensor arrays per original waveform on the Vietnamese test dataset, and I ran 1,000 simulation runs. For statistical testing, I measured the difference in false positive rates between simple inference and SAIL on both per run and per file scales. But let's see how the network did. At less than 1 million parameters, it achieved a 0.84 f1 on the validation dataset and a near perfect f1 on the smaller test dataset. Comparison with this field's leading work, or Katzis et al.'s pre-trained ResNet, the model is 93% as accurate while being 87% smaller. And SAIL achieved a statistically significant decrease in false positive rates on both the per run and the per file scales, with only minimal drops in recall and reducing the effective false positive rate from 14 per hour to 0. But I still wanted to know how the model would generalize to African rainforests and how it would change in confidence as distance or environment changes. The Elephant Listening Project had previously collected a dataset from the Central African Republic and the Cameroon, with over 2,000 recordings, hand-labeled with information about distance, gun type, environment, and more. I ran my model across all these different gunshots, plotting the distance on the x-axis and the model prediction on the y-axis, and using the width of the box plot to indicate how many gunshots were from that specific distance. Recall was as high as 78% for the half-kilometer bucket, and reduced and stabilized to around 57%, with a sharp drop at the 2.5-kilometer mark. Experiments like this can help us infer how far apart the sensors should be in actual deployment. As for the device, it not only has to be capable of 24/7 inference, but also long-term deployments and pinpointing of source sounds. So it would start with a simple filtering algorithm that runs 24/7, only using memory buffer, saving lots of power, and then only sending gunshot likely events to the microprocessor, where the lightweight deep neural network makes a more accurate classification. And if this also proves as gunshot likely, then communication with the cloud or other sensors will ensue, using a communication protocol that ensures that all probabilities from all sensors in the array are collected, allowing us to leverage sensor integration to confirm that it's actually a gunshot before finally sending an alert with sound and GPS location for verification. As I improve the model and continue investigating sensor integration, I'm excited to continue collaborating with the Elephant Listening Project to field validate sensor integration and the real-time gunshot localizing device. Thank you very much. If you have any inquiries, please reach out to the email on screen.
Okay. Thank you so much, Naveen. I will ask you quickly to come off camera so we can take some questions about your research. I'm gonna spotlight you.
It seems that I cannot start my video. Oh, there we go.
Oh, okay, perfect.
Okay, perfect.
Wonderful. All right.
All right,
Yeah, we
thanks
can go
so
into
much,
questions.
Naveen. I'm ready with some questions now.
For sure.
We have a couple in our Q&A that I'm going to read out.
hmm
First is from Avery. Avery's asking, what was your motivation for designing this system?
Great question. So I've always been passionate about the natural environment, the natural world. I've been watching like David Attenborough documentaries when I was younger. I even wrote him a letter, but the main motivation for this was that in 11th grade, I was doing a write-up on poaching, on illegal poaching in rainforests. And to do that, I had to do like research, get an annotated bibliography. And while I was researching it, I was like, wow. Poaching rates are actually rising in some areas, even though we have all this 21st century technology. And I started digging more in like how can technology and different sensors be used to mitigate wildlife poaching. And I also understood that it wasn't just a technology solution side. It's just there's the technology that can help with the solution, and there's also the economics and social based aspects of this issue. But I did see that there were some clear bottlenecks behind having acoustic monitoring as a solution to real-time rainforest gunshot poaching. So I just wanted to address that, and I've also been interested in like building things and engineering. So I just wanted to start that as a project, and um, I've been very, how should I say this? I'm really surprised at how far this has come. So I'm very grateful.
Well, it's so impressive, and yeah, it's been great to hear. And as we've been working on working with you and creating the materials for this press conference, it's been really great to read up on this as well. And yeah, thanks so much. Um, our next question is from Anashay. Anashay asks, are there any ways you can use multiple microphones with this technique to locate where a gunshot came from? And how much more computational time or power would that need?
Great question. Yeah, so there's two options to that. Either you have multiple different sensors separated by kilometers with very powerful microphones that can pick up the signal. And then when gunshot presence is confirmed by both one sensor and the central hub, which can either be another sensor or the cloud, that central hub will then ask for all the sensors to upload their waveforms, which could add at most around 2 to 3 seconds of latency for that uploading if you're using cell communication. And then with that uploading, it's a very fast computational method to have localization algorithms to have these three different waveforms or more, line them up, and then find exactly where the source sound is.
Great. Thank you so much for clarifying that. I have another question from Avery. It is, how widespread are these microphone sensors in the rainforest locations, and how difficult is it to monitor an entire rainforest?
It would be difficult to monitor entire rainforests. So the best strategy would be to employ strategically placed arrays at spots where you know there's easy entry to a protected area, unless you have the funding to cover the entire rainforest, in which you would definitely place more sensors. The range between the sensors and their effective coverage radius depends on a lot of different factors that can only be evaluated when you actually go out there and deploy it, like the environment type and how that affects the microphone pickup at different distances, other things like the actual microphone itself, and how powerful it is. But generally, at around what we saw by this experiment on the distance, a model can pick up the gunshot features up to around the 2 kilometer mark. So that could be a potential maximum distance between sensors, which would make covering like a 25 square kilometer area or more pretty easy.
Yeah, that makes sense. And we did have one more question in the chat, but you answered it when answering another question. So very efficient. Nice job. Um, yeah, this is really cool work that you're doing. So it's been really great working with you on it. Thanks so much.
Thank you.